Have you ever wondered what would happen if you could teach a machine every word from every book ever written? Well, that's pretty much the world of large language models, LLMs for short. These things are like mathematical prodigies that somehow wield probabilities like poets. So yeah, let's dive into this.
And the promise here, well, it was never just about creating a better search engine or a smarter autocomplete. The goal was always to build something far more profound, something that could reason, create, and interact in a way that feels, well, almost human.
So that's the big question, right? How on earth does a machine, a thing built on pure numbers and logic, achieve this extraordinary feat of generating what really seems like genuine thought? Let's start peeling back the layers.
All right, first things first, we need to get one thing straight. Well, these models absolutely appear to think. Their genius isn't cognition in the way we understand it. It's colossal, mind-boggling computation.
And you might not even realize it, but they are everywhere already. They're woven into our daily lives, helping us write emails, composing music, and even assisting doctors with medical diagnoses. They are fundamentally reshaping how we interact with technology. So, if you want to build a thinking machine, you have to solve a massive problem right at the start. How do you translate the rich, messy, beautiful, and often illogical world of human language into the cold, hard logic of mathematics? Now, this didn't just happen overnight, not at all. This was a journey built on decades of breakthroughs. It started way back with the idea that language could just be a game of probabilities, and it led all the way to the incredible architecture that powers today's most advanced AI. So where do we even begin? Let's get to the very first, most fundamental building block. Before a model can understand context or meaning or poetry, it has to learn how to do one simple thing: read. It all starts with a process called tokenization. You can think of it like this. It's how the machine breaks down our complex language into its essential digestible pieces, kind of like a machine's version of phonics or syllables. For instance, take the word unbelievable. The model doesn't see the whole word. It splits it into its building blocks: un, believe, and able. This is incredibly efficient, right? The model doesn't have to learn a billion different words. It just has to learn the common parts that make them up. Okay, so now we have these tokens, but on their own, they're just letters. We need to give them meaning, and that's where embeddings come in. They do something amazing. They transform each token into a set of coordinates, placing it on a vast, multidimensional map of meaning. And this map is absolutely crucial because, as you know, context is everything in language. Words like bank can mean completely different things. Embeddings allow the model to look at the surrounding words and place bank in the right neighborhood, either with geographical terms like river or financial ones like money. Okay, so we've got our building blocks: tokens, embeddings. The model can see words. But sentences? That's a whole other ballgame. To understand sentences, it needs a way to grasp context, relationships, and nuance. And this brings us to the architectural heart of modern AI. Then, in 2017, a research paper dropped with this incredibly bold title, and it changed everything. It introduced what's known as the transformer architecture, and with it, a totally revolutionary way for machines to understand language. What it did was introduce this wild idea called self-attention. It's basically a mechanism that allows the model to look at an entire sentence all at once and figure out which words are most important to every other word. It weighs all the relationships simultaneously. Think about this sentence for a second. John saw Bob. He waved. Now, who is he? Is it John? Is it Bob? For us, it's intuitive. For a machine, it's tough. Self-attention weighs the relationships, and based on trillions of examples it's seen before, makes a highly educated guess. But there's a catch. Self-attention is great, but it kind of scrambles word order. It sees all the words at once, which is a problem because the dog chased the cat is very different from the cat chased the dog. So to solve this, models use something called positional encoding. It's like adding a little mathematical timestamp to each word, so the model always knows the original sequence. So, we've got the architecture, the blueprint. But how does this thing actually get smart? How does it learn? Well, it turns out it learns pretty much the same way we do, through a whole lot of trial and error, just on a massive, massive scale. Let's use an analogy here, because it's a really good one. Imagine you're standing on top of a huge mountain, but you're in this incredibly dense fog. You can't see the bottom, but your goal is to get to the lowest point in the valley.
The model's goal is to find that valley, which represents the lowest possible error in its predictions. So it takes a tiny step in one direction and feels the ground. Is the slope going down? Good. Keep going. Is it going up? Okay, wrong way, change direction. It repeats this process millions and millions of times, always taking a step downhill until it eventually finds the valley floor.
And when I say this process is monumental, I mean, it's mind-boggling. We're talking costs estimated to be over $100 million to train a single state-of-the-art model. That requires massive supercomputers running nonstop for weeks or even months.
And why so much? Because the model is fine-tuning over 1 trillion parameters. You can think of these as tiny, tiny little dials. And with every single step it takes down that foggy mountain, it makes a microscopic adjustment to each of those trillion dials, gradually tuning itself towards near perfect precision.
Okay, so the model is powerful. It's incredibly smart. But that's not the end of the story. Not even close, because a powerful model isn't necessarily a helpful one or a safe one. The final and maybe the most crucial part of this whole process is aligning these systems with human values. So you've got techniques like regularization, which is like making sure a student actually learns the concepts for a test instead of just memorizing the answers. Then there's dropout, which randomly switches off parts of the model's brain during training to force it to build a more robust understanding. And most critically, there's RLHF, which uses real human feedback to teach the model what we actually consider helpful, safe, and appropriate. So when you step back and look at all these pieces together, the tokens, the embeddings, the attention, the trillions of parameters, what if we actually built here? It's so much more than just a piece of software. It's a truly monumental feat of engineering. You know, throughout history, humanity has created these incredible wonders that defined an era. The pyramids of Giza, the Apollo missions, and I think building an LLM, harnessing this level of data, computation, and pure mathematical insight belongs right there on that list. It's a testament to our ability to model one of the most complex things we know, our own language. And that really leaves us with the defining question of our time, doesn't it? As we build these machines that can process information on a scale far beyond any single human mind, the challenge is no longer just about computation. It's about wisdom. How do we make sure that these new thinking machines reflect the very best of us?
Thank you for watching. Don't forget to subscribe.